Okay, so we want to get into writing ionic compounds and names and formulas for ionic compounds. And there are a couple steps to do this, and let me walk you through those. So the first step is ionic compound means that something has transferred electrons. So it's gained or lost electrons. It's not sharing electrons. We'll get into covalent compounds, which is the sharing of electrons. But in this case, we have things that have transferred electrons. And this is always going to be something that's a metal, and it's combined with something that's a non-metal. So on the periodic table, this is shown I encourage you to go to ptable.com where this is shown. And there's this is color code, so all of my non-metals are going to be in this very corner of the periodic table, which is in this green and purple. So hydrogen over the left-hand side is kind of a special case, but we'll consider these non-metals. All my metals are going to be pretty much everything else that's on the periodic table. So notice there's a huge variety of metals. And whenever I combine a metal with a non-metal, they won't share electrons, they'll transfer electrons. And so I'll have something that will gain electrons, something that will lose electrons. The key to this is that it's going to gain or lose electrons until it's stable. So energetically, something is going to be stable generally when it has 8 electrons in its outermost energy level. And this is known as the Octet Rule. So if I look at something like my most stable elements, such as neon, that I can look at the electron configuration here. It's showing me it has 2 innermost electrons and 8 electrons in its outermost energy level. If I look at argon, again, I end up with 8 electrons in the outermost energy level. It can hold more there, but 8 is stable. Same with krypton. So krypton, I end up having a very stable molecule, or stable atom, and it also has 8 electrons in outermost energy level. Again, it can hold a lot more there, but 8 is very stable. So it turns out that arrangement of 8 electrons, so they're spin paired and their waveforms interacting with each other, that's a very stable configuration. So any atom that can have 8 electrons in the outermost energy level is going to be stable. So if I look at something like fluorine, it has 7 electrons in its outermost energy level. If it gains 1 more, it has 8 and is very stable. So fluorine has a tendency to gain 1 electron. In fact, a strong tendency to gain 1 electron. And it'll rip those away from metals that are able to give up electrons more easily. And you notice that there's this pattern here. So fluorine has 7 valence electrons, it'll gain 1. Chlorine also has 7 valence electrons, it'll gain 1. Bromine, guess what? 7 valence electrons, it'll gain 1. So this whole group, we'll call it the halogens, is highly reactive because they really are scavengers for electrons. They're desperate to have 1 more electron, so then they'll be in a stable state. Notice I go over oxygen here. So oxygen has 6 electrons. To get to 8, it's easiest to gain 2 electrons. Same with sulfur. It has 6 valence electrons. To get to 8, it's easiest for it to gain 2 electrons. When I get to the other side of the periodic table, I look at something like lithium. So lithium has 1 electron sitting in its outermost energy level. It's most likely going to lose that electron. And then it'll have the 2 in the innermost electron. So that first layer can only get 2 electrons in there. So 2 is stable at that first layer. So things like lithium, when it loses an electron, will be stable. Helium by itself has 2 electrons in the innermost layer, so that's the first layer. It can only get 2 in there, and it'll be stable with that. But this is the idea that we're going to get into. So we're going to make ionic compounds by shuffling electrons around, and those electrons have to come from someplace and go to someplace. So we need to balance those moving electrons to make sense out of what will be a good formula and will be a good name for these things. So let's go to the Lewis dot diagrams as a good way to think about this. So I'm going to think about fluorine here. So I'm going to draw fluorine as and I'm going to combine that with, I don't know, say sodium. Then we'll get to something that's a little more complex. So I may combine sodium with oxygen. And then I'll get to something that's a little bit more complex where I'll combine, I don't know, magnesium and nitrogen. So let me go through these 3 examples for how to think about it, and then I'll give you a shortcut. We'll call it the crisscross method to figuring out formulas. But let me walk you through what's happening with these. So let me pull up a piece of paper to draw on. So here we go. So these are 3 that I want to look at. So again, the Lewis dot diagrams are a handy way to look at these things. So I'm going to think about sodium. Sodium, I'll look at the valence electrons. It has a single valence electron. Fluorine, if I look at it, it has 7 valence electrons. So if it has 1 more, then it's going to be stable. So all I need is 1 sodium to give 1 electron, and then I'm going to be left with sodium which now has a charge of +1, and I'll indicate a charge in this way with brackets. So notice when it started, it had the same number of electrons and protons, so protons inside the nucleus. So it's lost 1 electron. So when you lose an electron, you end up having more protons than electrons. In this case, I'm going to end up with a positive charge. Fluorine has done the opposite. So now it's gained electrons. It's got all these 8 electrons on the outside, and it has a negative charge. So notice both of these are stable now. So it only took 1 sodium and 1 fluorine. So when I write a compound out of this, I'm going to say, well, this is sodium and fluorine come together. And when I name this, I'm always going to put the metal first, the thing that's on the left side of the periodic table. And I'll give it a name. I'll call this sodium. So my cation, the thing that's positive. So cat is C-A-T, has a T in it, so it's positive. So my cation is going to keep its original name. But my anion, the thing that's negative now, I'm going to change the ending to IDE. So this, instead of being fluorine, this would be fluoride. So IDE ending. Let me go through a couple more examples of this, and this is what I'm asking you to do: is to be able to look at these compounds or look at these elements and be able to figure out which what is the name, the formula for these. So let's look at sodium and oxygen now. So sodium again has 1 valence electron. I want to combine that with oxygen. So oxygen has 6 valence electrons. So 1, 2, 3, 4, and I'll pair them up, 5, 6. So sodium now, it'll give an electron up, but it only has 1 that it wants to give up. So there are core electrons. There are more electrons there. Remember, we're just showing the valence electrons. But those core electrons are stable. It's only going to give up its valence electrons. So it gave up 1, but oxygen now only has 7, not 8. So I need to take a second sodium and have that give up another electron. And now my oxygen will contain 8 electrons. So notice what I've done. So now I have a sodium that has a positive charge. I have a second sodium that has a positive charge. And I have oxygen now, which has its 8 electrons and is very stable. And this has a -2 charge. And this is how I represent this. So when I write a formula, right, I have 2 sodium for every oxygen. So this is a ratio. I have Na2O. And when I name this, I'm going to name my metal first. So this is sodium. And my oxygen, I'm going to change the ending to an IDE. So it would be sodium oxide. So these two things mean the same thing. They represent these ions, this cation, or positively charged ions of sodium, these anions, the negatively charged ion of oxygen. And it gets there by thinking about how the valence electrons have been shuffled around, so you end up with 8. So it's sodium, those things that have fewer than 4 electrons, it's easier to shift those electrons. Those things that have more than 4 electrons, it's easier for them to add electrons, and that's what they do. Okay, let's get to something that's a little bit more complex. There's a shortcut here, so you may notice, right, this 2 happens to be the same number as the charge on the opposite atom, and this is telling me I have 1 oxygen, so that's the same as the charge on the sodium. So there's a shortcut method. So sodium always takes a charge of +1, and oxygen always takes a charge of 2-. And if I use that charge, it'll help me figure out the formula. So this would be Na2O1, meaning that I have 2 sodium and 1 oxygen. When we get something more complex, so I'm going to take magnesium, which has 2 valence electrons, and I'll combine that with nitrogen, which only has 5 valence electrons. 1, 2, 3, 4, 5. Well, what happens here? Well, I'm going to move electrons. So this is my metal. It has fewer electrons. I'm going to move one here, move my second one here, but now, good grief, I'm only at 7 for nitrogen. So I'm going to need another magnesium. I'm going to take another magnesium. It's going to have 2 electrons. I'll move this one here, but oh, good grief, now I've got another electron on magnesium. What do I need to do? Well, I need another nitrogen. So I'm going to have 1, 2, 3, 4, 5. I'm going to take this one here. Oh, good grief. Now I've got more here, so I need a third magnesium with 2 valence electrons. And I can move those electrons so that I end up with 2 nitrogens, which have 8 electrons in the outermost energy level, and I have 3 magnesium. So when I write my formula for this, this is going to be magnesium with 3 of them and nitrogen with 2. Okay. When I name this, I'll call this magnesium, and nitrogen becomes nitride. IDE ending means that it's in a compound. So the shortcut that I can do with this, right? So magnesium, it takes a charge of 2 plus, and nitrogen takes a charge of 3 minus. Right? So I can use this crisscross method to figure out that magnesium must have the charge of 3, or I must need 3 magnesium and I must need 2 nitrogen. Anyway, handy. There are a bunch of different ways to think about this, and there are other videos out there that describe the naming of ionic compounds. I encourage you to take a look and read about it and get your head around it. We're going to be using a lot of ionic compounds, and you'll need to know how to name them and also what the name means in terms of the formula. Hope that helps. Talk to you soon. Bye.